let's look at a new topic: sacrificial protection of metals. According to the syllabus, this is the learning objective. These are the learning objective. Describe and explain sacrificial protection in terms of the reactivity series of what metals. So let's look at this is the reactivity series. You can see potassium, sodium, lithium, calcium, magnesium, aluminum, zinc, iron. Then you have other that is below it. You have what? Tin, lead, hydrogen, iron, that's the proton from the water or the acid. Then you have copper and the others. But most especially the metals that are more reactive, that are above iron in the series. You can see them. You have potassium, you have from potassium to zinc. All these materials are to be made the word anode. But this and this and this, since the electrolyte contains water, and this metals dissolves in water to form alkaline solution. These ones are used because they are less reactive with what? Water. Less reactive with what? Water or moisture. So the magnesium, aluminum, and zinc are the best choice, known as what we can call it what? The mass. The mass. MAZ. Now, if you look at iron will be made the what? The cathode. Right? Will be made the what? Cathode. So this is the reactivity series. So the metals that are above iron are the more reactive one, and they are to be made the what? Anode. And those ones that are below iron are never what used. They are never used. So it is the iron. So iron is the material to be protected. It could be iron or any material that contains what? Iron, like what? Steel. It's an alloy. So it could be iron or what? Steel. So all these ones are the what? Materials or object we made as the word anode. The iron itself or steel, so we made the word cathode. So I'm going to sacrifice these three especially, not this one. We don't use this. It's either this or this or this. So I'm going to sacrifice either of those three to protect what? Iron or steel. So take note of that. According to my diagram, you can see that the object or material to be sacrificed is made the word anode, which could be, as I said in the reactivity series, it could be what? Magnesium, aluminum, or zinc, right? And that is where electrons start to flow. Electron flow from the more reactive what? Element to the less reactive element. Of course, there should be a wire or a conductor, a cable, to connect the anode to the cathode so that there'll be a flow of what? Current. So this is a wire, an electrical conductor, to allow electron flow from the more reactive elements or material, that is the anode, to the less reactive one, and that is the word iron. So it flows through iron and it goes into the ions in the electrolyte. And as you can see, if you look at the diagram closely down, you can see that the electrolyte there, the electrolyte is, electrolyte could be any of this, could be that these two metals are submerged, whether partially or fully, in what? The soil, which contains what is moist, contains water, or on the sea, right? Contains a lot of salt water. And definitely you have here water. Water is there. The ions, hydrogen is there, right? Let's say the salt. See sodium. So you can see this. So you can see the hydrogen, which is less reactive than what this will be discharged. So the electrons that is lost by the anode is passing through the ion but taken by the proton or hydrogen ion, and you will see bubbles around. Bubbles will be seen around the what? Cathode. Bubbles will be around here. bubbles. That means the ion does not receive the electron for reduction. Instead, it is the hydrogen ion inside the moist soil or salt water that receives it, and it is reduced to its what molecule, or as what hydrogen what gas. I'll write the half cell equation to show you the summary of the equation. Just know that the diagram is of paramount what importance. Understanding the diagram, that the anode should always be the material to be sacrificed, right? Sacrificed, and the cathode should be the material to be protected, and that material is either iron or steel. Iron or steel, and the electron flow, that should not flow from the more reactive one to the less reactive one. If you look at the diagram very closely, it is like an electrochemical cell. There's a potential difference between what iron and what any of the materials. Any of the materials. I can use magnesium against what iron. I can use aluminium and iron, or it could be what zinc and what iron. The more further apart they are, the more the potential what difference. So this one will have the highest potential difference because they are further apart. Because they are further what apart compared to what the difference between what iron and what. Now the choice of material among these three metals, magnesium, aluminum, and zinc, matters. Now if you have to connect magnesium and iron, or aluminum and iron, or zinc and iron, which of them will have the highest potential difference of voltage produced? The principle lies in the fact that the further apart the metals are from each other, the higher the potential difference or the voltage produced. So if you look at the reactive series, you will see that iron and magnesium are furthest apart. Iron and magnesium. This is iron and this is what magnesium. So you should have the highest potential what difference. The highest potential what difference. So the difference between, you have magnesium and iron, they have aluminium and what iron, then zinc and what iron. So this one is furthest what apart, right? So this is the closest. So this one will have the lowest potential difference. So will have the what the highest. The PD here will be what the highest. This PD of voltage will be the what lowest. So the potential difference. So it's like an electrochemical what cell. The advantage of this process is that you don't need a power supply, you don't need a battery. It is a spontaneous what reaction. So the reaction can start on its own, especially when you have two different what metals with different electrical potential. So electron will flow from the more reactive one, which is invariably made the anode, to the less reactive one, which is invariably made the word cathode. So invariably you are protecting the cathode from where? From corrosion, iron rust. Why are you protecting the cathode? So why cathode protection? Is to prevent iron or steel from what? Rusting or corrosion. That's why we all know that since the iron does not undergo what? Oxidation by losing electron. Instead, the more reactive one is the one losing what? Electron. So this one is undergoing what? Oxidation. Iron is neither, iron here or steel is neither undergoing oxidation nor reduction. The electron lost at the anode is received by what? The hydrogen ion, the ions inside here, right? The protons here, or hydrogen ion, inside these what? Electrolyte, and it's that is being what? Reduced as what? Hydrogen what? gas. You see the bubbles coming out. So it is the hydrogen ions inside the electrolyte, be it in the moist soil or salt water, that receive the electron and is being what? Reduced, and not what? Ion. So electron lost at the anode is received by the ions in the electrolyte. So ion here is neither undergoing oxidation nor reduction. So ion is not losing, it's not what? Gaining. It's not being reduced, it's not being what? Oxidized. So ion will be what? Protected. The size remains what? The same. It does not decrease in what? Size. Let's look at what really happened at the anode. If I'm using like zinc, there's zinc. Zinc loses electron. You can see from the diagram, and zinc become what? Oxidized. Zinc is oxidized. Oxidation has taken place because electron lost or increased oxidation number. Oxidation number here is neutral, or this element is 0, and here is +2. So there's an increased oxidation number, or electron is what? Lost. Now this oxidation happened at the what? Anode. Then at the cathode, let's look at the cathode half cell equation. Now, as I said earlier, electron lost at the anode received not by the ion but by the what? Hydrogen ion. So this is the hydrogen ions in this salt water or in the moist soil. So it is received. Plus means receive, minus means electron lost, electron what? Gain, and this become the gas. So that's the hydrogen gas. So ion is what? So these are the half cell equation. These are the half cell what? Equation. So electron lost at the anode received by what? The hydrogen ion in the electrolyte to be discharged as hydrogen what? Gas. So pretty soon, if you look at this, this is the half cell equation for both anode and cathode what? Reaction. If you look at the application of sacrificial anode cathode protection, iron, steel, or oil rigs. In iron, steel, or oil rigs, the iron or steel does not rust nor corrode, because zinc corrode with preference to the iron by losing electrons to the hydrogen ions in the electrolyte, and not to the what? Ion as the what? Cathode. Therefore, the ion does not receive nor lose electron, no reaction, and no decrease in size. So that protects the iron or steel in oil rigs, submerged in the ground or fully submerged in the soil. As you can see, one of the applications of sacrificial anode cathode protection is applied in protecting iron oil rigs made of iron and or steel. The iron or steel does not rust, corrode, because zinc corrode with preference to the iron. It does this by losing electrons to the hydrogen ions in the electrolyte. Therefore, the iron or steel does not receive nor lose electron, no reaction. If you don't receive or lose electron, that means there's no reaction and no decrease in what size. So therefore, the cathode or the anode, the cathode is protected, which is made of what? Iron or any iron what material. Examples like what? Steel.